Hello and welcome to the fourth part of our lecture. In the previous part of the lecture, we discussed how to synthesize MIPS and how to use them into senses. However, we mainly focused on the synthesis of receptors for small molecules, chemicals such as hormones, neurotransmitter, drugs molecules, pesticides. What happens if you want to imprint a bigger entity? What happens, for instance, if you want to detect bigger entities such as peptides, proteins, viruses, or even whole cells or organisms such as bacteria? They can sometimes be bigger than the MIP particles that we typically make ourselves. So that doesn't make sense. You can't make a MIP particle around one singular bacterium and expect it to work. I mean, like that's not really practical. On top of that, we usually work with organic solvents, and most of these biological entities, the macromolecular entities that you want to dissolve in these organic solvents, don't survive. So you will kill off your target before you're even starting to polymerize your polymer. A solution lays in the development of surface imprinted polymers, which are a very special kind of MIPS, and these we call, in our lab at least, we sometimes call SIPs to distinguish between macromolecular MIPS and the MIPS made for smaller molecules. Now, the easiest approach to make SIPs is an approach that uses self-assembly or electropolymerization, like we explained before, for the smaller molecules. You basically just take a reaction mixture with your monomers inside. You also dissolve your target in it, and then you deposit that onto a substrate where the polymer will grow either through self-assembly or through directed self-assembly under the influence of an electrical field and electropolymerization. The only difference is that when you extract your MIP, the target is going to be too big to penetrate into the bulk of the polymer and can only bind to the surface anymore. So that's the only difference between these type of SIPs and the traditionally made MIPs. Now, this is a very valuable technique that was used by a group in Japan by Tokonami and his co-workers. And what they did was they took a charged solution of electroactive monomers and dissolved that in an aqueous solvent along with the target, in their case the bacterium P. aeruginosa, and through electropolymerization they deposited the MIP onto a QCM electrode. And a QCM is what we referred to earlier as a physical, very sensitive microbalance, a physical transducer that works based on changes in mass on the surface. So a microbalance, the word says it itself a little bit. It is a very sensitive balance that can measure entities in the micrometer range, in this case bacteria. So what happens is in QCM is you use a gold electrode and you deposit that onto a quartz crystal, therefore quartz crystal microbalance. And these quartz crystals are piezoelectric. This means when you apply an electrical field over them and a changing alternating current, they will start vibrating. And they will do so at a certain frequency that is constant and is called the resonance frequency. Now, whenever bacteria, in this case, bind to the surface, the mass on the surface uh, will increase. And of course, when something becomes heavier and at the same energy, it will take more energy for the crystal to shake, but you only have a limited amount of energy that you put into the crystal. So what happens is it will start resonating at a lower frequency. It will start vibrating slower. And as you can see in the graph on the top left side, this will this effect will become bigger as the concentration of bacteria becomes bigger until you have about a billion bacteria per milliliter. If you increase the concentration even more after that, nothing will happen anymore. This is because all of the binding cavities have been filled with bacteria, and adding additional bacteria won't result in more bacteria binding to the surface and also no change in signal. You might also notice that the layer is about half the size of the bacteria, which is on purpose, because if you make the layer too shallow, then also the cavities will be too shallow and basically anything can bind to them. If you make the layer too big, then basically the polymer will be bigger and all bacteria will be buried and engulfed inside the polymer and you can't get them out and nothing can rebind to it anymore. So this just shows you that one of the disadvantages that you really have to tweak your parameters to get exactly the desired thickness for your polymer layer here. Now, like I said, the advantages are that you can directly deposit polymers on top of your chips. Upscaling is possible for mass production. You can imagine having a very large electrode, and on that electrode you deposit through electropolymerization a large sheet of a zip layer, and then you just cut that into smaller pieces and you have a mass production system. What is a drawback is, like I said, it's difficult to optimize the parameters and to get exactly the right layer thickness, and it's only usable when your reaction mixture is not cytotoxic, so it can't kill your target, it can't kill your viruses, your bacterium, your cells, your proteins, whatever you want to detect. An alternative approach is to first immobilize your target onto a substrate, then add reaction mixture and form it around that substrate. When you then remove the template or remove the polymer or remove the substrate, you'll have a MIP with exactly these imprints of your target. Now, we collaborate with the University of Newcastle in the United Kingdom, where a colleague of ours works, and we also collaborate with a company that makes commercial MIPs for sensing purposes called MIP Diagnostics, which is located in Leicester. And they have a very specialized solid phase extraction molding technique to make these SIPs. And this solid phase extraction is very comparable to what you have in column chromatography, which we discussed before, is that you have a stationary phase. And onto that stationary phase, they've immobilized their targets, and they usually use proteins. And what they do then is take their mobile phase and take their polymerization mixture and put that in the mobile phase. They add heat, so the polymerization occurs, and then they open up the column, and at first only the MIPS with a very low affinity for the target will come off the column. They basically will throw these nanoparticle MIPS away because they don't have much affinity for the target. Then they will add a solvent or a or water at an elevated temperature to break the bonds between the protein, the target template, and the forming MIPS. And these MIPS will be the high affinity MIPS that they actually use. These will then be put on a sensor, and they use this in combination with an SPR to detect the spike protein in COVID particles. And they notice that when they do so, they are able to detect COVID in very, very low concentrations. And these results have actually been the basis for a rapid test for COVID that's coming out later this month in the UK. On top of that, we collaborate with them on a publication in 2018 in nanoscale, where we did the same thing for proteins that are markers for heart failure. And we've shown that we can actually detect these in a very specific manner in serum, which opens up the possibility of using our sensor solutions to prevent people dying from heart failure by diagnosing it at a very early stage and preventing it from happening. Now, molded SIPs have the benefit of being able to be used for mass production, especially if you use the SPE system that MIP Diagnostics use. They can make multiple kilograms a day of a certain MIP. There is no need for template removal, and you get very homogeneous particles because you toss the low affinity ones away. The ones that elute first from your column, you just throw away. The ones that only come off after you add a solvent or an extra, or you heat the water to wash them off, you keep. So that's much more homogeneous. The disadvantage is that you need to be able to immobilize your target onto the SPE column, and you can't use organic solvents, which is a very big disadvantage because usually polymers are made in organic solvents. Now, if you want to do that, there is a solution for that, and that's our third main route to make surface imprinted polymers. And this is what we call micro contact printing. And this is the approach that we have the most experience with in our lab. And it's a very simple approach in which you just take your polymer and your monomers, your cross-linker and your initiator, you dissolve them into a substrate and you let them pre-polymerize. And when they become jelly, you spin coat them up onto a substrate where you basically just spin the substrate, put a drop of polymer onto it, and a nice flat layer will be deposited onto your substrate. Now, this polymer is not fully polymerized yet, so it's still soft enough to be deformed, but hard enough to form a rigid layer. So what you can do then is take a stamp, immobilize a monolayer of cells. In our case, we use the coli a lot, and push these cells into the layer. And the layer, like I said, is still soft enough, will deform, and will make molds around these targets, around these E. coli for us. Now, when you polymerize the mixture, the layer will become hard overnight, but will also interact non-covalently with functional groups on the surface of your target. These can be proteins that are specific for a bacterium. These can be carbohydrates that you have on a bacterium. In any case, it will create a functional match next to the already morphological match that's already there. When you then exposed these SIP covered chips to a mixture of a complex mixture of small molecules and bigger entities, only the E. coli will bind to your layer and will cause a signal. Colleagues of ours at Leuven University did a similar study where they imprinted multiple bacteria, including Campylobacter jejuni. And Campylobacter jejuni is a bacterium that occurs a lot in the food industry in chickens and that kills chickens and makes their products, both meat and eggs, unusable for human consumption. But it's very difficult to detect whether a chicken is infected with Campylobacter jejuni. So the food industry has asked us and Leuven University to develop a sensor that is able to detect Campylobacter by just analyzing feces of chicken. So what we did was we imprinted that Campylobacter jejuni, which you see on the top left side, and that makes an imprint that's pretty similar in size and shape to the Campylobacter. And we use that in a detection experiment using a thermal resistance measurement, which we'll explain in the final part of our lecture. And what we saw is that we can very selectively detect whether there are bacteria in the chicken feces, and that is not so special because all feces samples will contain bacteria, but more specifically, if there's also Campylobacter jejuni present, and that is very relevant because the food industry could be able to use such a sensor in the future to prevent food from being wasted, to prevent chicken samples from being destroyed. Now, a similar invention was done by a group that we know in Vienna, in Austria, the group of Peter Lieberseit, and they made a similar MIP on top of a gold electrode that was used for the quartz crystal microbalance measurements, and they used that to imprint E. coli. And what they did was they imprinted E. coli on top of the QCM electrode and then used a very simple flow cell, which you can like manually add water to analyze water samples for the presence of E. coli. And this way, obviously, you could use such a tool for environmental screening. So there's lots and lots of possibilities for using these type of SIPs. Now, the benefit of using micro contact imprinted SIPs is that the synthesis is very straightforward. It's compatible with organic solvents, but it still requires template removal. Automatic mass production can be difficult, and templates can be very heterogeneous because you imprint them by physically stamping these cells into the layer. You can imagine that one person might push a little bit harder than another person. You can also imagine that you would do manual labor, so that's not really good for mass production. This is where engineering kicks in. We know an engineering group in Hull University in the UK, the group of Vasily Paunov, that found a solution for this. What they did was they took the cells they wished to detect first, and as you can see in the figure B, they made cell suspension and used a functionalized glass substrate and made a nice monolayer, an EVA film of cells on top of that glass substrate. What they then did was they used a silicon called PDMS, which they cast over the cells and which will adapt the form of the cells. They cured this PDMS, making it hard, and peeling it off. And what you have is a negative replica of your cells that you wish to detect. So you have holes that match the cells in size and shape. Now what you can then do is take another polymer, pour that over the PDMS, cure that polymer, and you have a stamp that has exactly the same dimensions and also some of the functional groups that your original template cells have. And what you can now do is take that master stamp and put it into a roll-to-roll coater, as you see at the bottom picture. Now, a roll-to-roll coater takes sheets of a polymer and passes that over multiple rolls. Now, if you let that roll-to-roll coater glide over this master bioimprint stamp, then you will create stamps as you go along. You will literally create a production belt making large sheets of MIPS. Now, if you can deposit these imprinted sheets of MIPS onto substrates and you can cut them into pieces, That is where you can use micro-contact imprinting for creating SIPs on a large scale. So this is a very clever way of doing so. The only drawback here is that you lose functionality, right? Normally you imprint the cell, so you have all the carbohydrates, the proteins on the surface of the cells. You will lose some by making a negative master first and then a positive master. So you will lose a lot of functionality. So we'll be a little less specific. Nevertheless, a very cool idea that will get us one step closer to industrialization. Now, within our lab, like I said, we have a lot of experience with making these type of SIP-based and MIP-based sensors, and we're also looking at how can we market them. And this will be the subject of the case study, and this will be also be the subject of our final part, our fifth part of the lecture, which I will invite you to now. And I will see you later. Thank you for your attention, and hope to see you in part 5.